right, so I think we're going to start with atomic composition right on time here. It is my pleasure to introduce Monroe from Qubits and IonQ, who's going to talk about quantum computing with atoms and photons.
Okay, thank you for the kind invitation to this meeting, which is it's every 6 years, so it's always a special event. And for me, I'll drop a hint a little later about some history that I've had with this meeting. That was very wonderful. So I will speak mostly on behalf of my research group at Duke University, but I'm also kind of affiliated with IonQ, a company I founded a long time ago, and I'm more on the research and development side of that company. And as you know, IonQ is building quantum computers in an industrial fashion, whereas we're at Duke doing sort of parallel work, obviously much more in the research fashion with I don't know, 1% of the budget, things like that. So things that we're used to do at universities. So in the spirit of, this is a tutorial, I don't typically go to some of the fundamentals in some of the work that I'm involved with, but I will do that after this intro slide, which as an experimentalist, I'm very interested in the connections between the different types of potential hardware, and don't read the fine print too much. I stole this from a Science magazine article about 10 years ago that was reviewing the many platforms that look compelling to build a quantum computer. So these are obviously systems that have excellent quantum control, isolation of individual qubits. It doesn't have to be qubits, but that's sort of where we are now. And all of these platforms, they have their own piece of exotica, either really low temperature or really low vacuum. And I actually split the columns in a different way than the original. I put generally the solid state platforms on the right, and the atomic AMO platforms, atomic, molecular, and no molecules here, but atomic optical platforms on the left. And what I find interesting about these two divisions is that they have really different approaches to the field, but also really different challenges, I think. The solid state platforms, I guess superconducting loops have probably been built most mature in terms of building into systems, because they do behave as wonderful isolated quantum bits, if large. And some of the other platforms, this morning we heard a lot about other solid state platforms where you can wonderfully localize individual quanta in things like silicon or other materials. Even diamond has some interesting defects that can have quantum control. And I think the progress of these fields is pretty amazing, and I think it's obviously leveraged by the industry of fabrication of silicon and other solid-state devices. And so in the future, we all look forward to a solid-state quantum computer where we can sort of use the tools and scale almost indefinitely. So I'm working on the other side here, which has an entirely different challenge. So I call these synthetic qubits and these natural qubits. That's a little bit biased, I suppose, but the nice thing about synthetic qubits is you can build them. But I might argue the nice thing about natural qubits, like atoms, atomic ions, molecules, electrons, single photons, the nice thing about those platforms is that you don't have to build them. They sort of come for free as a unit, but the real difficult problem is you have to control them because they can't be stuck to a solid on a surface or in a solid. They can't even be in air. You have to get very low levels of vacuum. So isolating natural quantum bits is really an interesting pursuit. We don't worry about certain things like scaling, I should say, because all atoms are the same if they're well isolated. We worry more about the engineering, and this usually involves not always optics, microwave, RF, electromagnetic fields, and vacuum. But if you have a high vacuum, I've always hated that high vacuum. If you have a really low vacuum, then the atom is very well isolated, and you don't need to even cool the system. So you can run many of these natural quantum systems at room temperature because of the conduction from the room temperature really doesn't affect you very much. Okay, so this is sort of my thoughts on the world of the different platforms. And what's wonderful is that they're all sort of housed in physics, But I think we really need help from engineers and surface scientists and all kinds of different branches, chemistry for sure, to actually build these things. Okay, so enough about that. I guess I'll concentrate on the trapped ions, which I'm here for. And in a sense, and there's some footnotes, I won't read all the fine print, but in a sense, the trapped ion system is really the cleanest quantum system we have. And I say that because, again, they're isolated with vacuum, they're electromagnetically trapped, and the important thing is they're trapped based on their charge, and everything inside the atom, like the qubit, the thing that you really need to keep control of, is inside the atom, and it has nothing to do with the charge. So just by trapping an ion, you don't affect the internal states. That's actually not exactly true for neutral atoms. You get a lot more neutral atoms, and we've heard from Kenji this morning, and tomorrow Misha Lukin will talk about that platform. You get lots of them, but because they're neutral, to trap them, you have to distort them with a dipole force or something like that, and you have to take great care to make sure you're not disturbing the internal workings of the atom. But other than that, atoms and ions are, once you get inside the atom or ion, I call ions atoms as well, they're really the same in terms of being able to read out quantum information, the way you execute entangling quantum gates and so forth. Lots of similarities. And one commonality on the hardware side is that we almost always use lasers, optics, to work with these atoms and ions. Of course, this is sort of a culmination of the last 50 years of using lasers to control all different regimes of atoms, from laser cooling to ultra-fast type excitations. So all of those tools come to bear. So anything involving coherence and optics applies very typically to atomic platforms for quantum computing. So this picture is a lovely ion trap that is built out of, it's a very complex silicon device built at Sandia National Labs. They have a wonderful quantum computing group at large, including an ion trap group. And this is a very complicated chip. It has many layers. I won't get into it, but there are about 100 electrodes. They're painted with gold. They're plated with gold at the very end so that we can apply potentials that create electric fields that suspend atoms. And these atoms, there's exactly 80 of these atoms in this picture. These atoms are ytterbium-171, and they're floating about 1/10 of a millimeter above that chip. The chip is maybe, I guess the interposer here is maybe a square centimeter. So from left to right, they occupy a space of maybe 1/2 millimeter. So divided by about 100, that's about 5 micron separation between them. We can obviously resolve them optically. We're shining light on these guys, and they're fluorescing at the very particular wavelength of the S to P transition in ytterbium. It's at 370 nanometers, so we have a UV-sensitive camera to see that. What else did I want to say? Yes, the qubit is stored inside the atom. I'll talk a little more about that in a second. But these atoms, once they're trapped, and don't ask me how you trap them, there's a lot of black magic and so forth. You can imagine how that works. It's kind of straightforward. Not like rocket science. It is actually straightforward. I mean, you ionize a neutral atom, and in the presence of the electric fields, it feels trapped. So you know, there's a lot of work that goes into designing the geometry of these ion traps. But even that's a very old area. If you know what a mass spectrometer is in a vacuum chamber, that's basically an ion trap in 2D. So the technology's been there, many Nobel Prizes and so forth, for many decades. Let's see, what else did I want to say? Okay, well, the atoms stay there for a long time. If the chip is at room temperature, the atoms, a chain of this size might stay for an hour or so, and then a collision with the residual background gas will generally, all the dominoes fall and you have to load again. If you cool this thing to 4 Kelvin, which is very easy to do these days, in even a closed cycle cryostat, then the lifetime is pretty much indefinite. It's months. As long as you have the power on, they're there. So I don't want to call this a solid state system, but it's very stiff. And through laser cooling, the atoms are very well localized to about 1/1000th of the size of the diffraction limited spots you see, about 1 micron here. And they're localized to maybe 1/100th, 10 nanometers or so in space. Okay, with that background, actually a little more background. Why ytterbium, you might say? I wouldn't have guessed this, I guess, when I was in high school or something, but ytterbium actually is very much like an alkaline earth. If you look here, it has 2 s electrons. And so the alkaline earths with 2 s electrons, once you ionize once, you have a very simple electronic structure akin to the alkalis that we use for neutrals. And of course, there are these transitional metals that also have the right structure. So the ones I've boxed here are typical atoms, atomic ions that we trap and laser cool. And the reason we need the simple atomic structures is so that we can drive cycling transitions and transfer lots of momentum from light to these atoms. And the energy level structure, this is ytterbium-171 in particular, but they're all very similar. There's some differences. We typically store the qubit in the ground state hyperfine levels. And that's good because levels like this, if you pick them right, they're very good atomic clocks. And that's the statement I mentioned, that every ytterbium-171 is the same. That's why we use them for clocks. They're standards of time. So there are certain things that we don't have to worry about when we scale up atomic quantum computers. So this transition here from S to P is the dissipative one. It allows us to prepare the states and measure the states. That's called SPAM, state preparation and measurement. We collect fluorescence, and we can tune things with selection rules and polarization sometimes so that only one of these 2 states, one of these 2 qubit levels fluoresces and the other one doesn't. And so the bright dark tells us unambiguously what state we're in. Now, many of these ions actually have a metastable low-lying D state, or even in ytterbium's case, there's an F state, and they have very long lifetimes from on the order of a second to on the order of a minute, typically. So you can actually store information up here if you need to. And you might want to do that in the future if you want to use very narrowband lasers instead of microwaves. Okay, so let me, again, in the style of a tutorial, I want to go through some 101 physics of ion trap gates and ion trap quantum computers. So the most difficult part, and this is true for most platforms, of making a quantum computer is to controllably entangle, say, any pair of qubits in the chain. And so if this is a chain of ions, they form a crystal because they repel each other, and we're trapping them at the same time. So they form a stationary crystal. Now, we would like to entangle 2 of these atoms, say that one and that one. So we shine laser beams. These are actually optical tweezers. They apply a dipole force that we turn on and off, not for trapping like in neutral atom systems, but to modulate the trap and affect entanglement. The idea here is that this force, it's really a dipole force, so it's a classical laser beam hitting both atoms, but the force has a quantum part to it, and that is through selection rules, it depends on the system. The direction of the force depends on the qubit state. You can do this. There are many ways to do this. I want to be kind of general here. But we will assume that if the qubit is in the state up, it moves up. If it's in the state down, it moves down. Easy to remember. So if both atoms are in the state up, under the influence of this force, they move up together. Their separation stays the same, and therefore their Coulomb energy stays exactly the same. If they're both in down, they move together. But if they're in the opposite parity states, up, down, or down, up, they're a little further apart. They're on this hypotenuse, this little diagonal, and there's a slight energy defect in their Coulomb energy that looks like a 1 over r cubed, where r is the separation. This is a dipole-dipole type interaction. It makes sense because we're smearing an atom out in general in 2 places. We're making electric dipoles, sort of like a p orbital in hydrogen, if you want. And we'll get a dipole-dipole interaction, falls off like 1 over r cubed. But this energy gap is really useful if we think about it in terms of Boolean logic of the qubit states. There's only 4 possibilities. I just told you if they're the same spin state, nothing happens. But if they're in different spin states, their energy changes, and in quantum mechanics, that means there's a phase shift. In this case, it's a double spin-dependent phase shift. And it's the same phase shift if you're up, down, or down, up. Because the distance, yeah, right, they're a little further apart no matter what configuration. So if we set this phase to pi over 2, I won't go into detail here, that turns out to be a really interesting gate. And it's nonlinear right off the bat. You can tell it's nonlinear because what happened to up, up is not a mere product of what happened to down, up, and up, down. Right? If we had opposite signs in these phases, then it would be boring. That would be a linear gate, no entanglement there. But this is as expressive, as powerful as a C0 gate, which is sort of the basis that we use, at least quantum algorithmists think about It's sort of how you entangle 2 qubits using a CNOT gate. And that's how we do it, with laser pulses. I should have obviously acknowledged the many folks who sort of put this picture together. It started in 1995. Chirac and Zoller recognized that you could, in a different regime, you could use the modes of motion coherently. It required that you cool to the ground state of motion. I'll get a little more into that. And then Anders Sorensen and Klaus Malmer showed the much improved version that didn't require ground state cooling. And that's closer in spirit to what I talked about, really, spin-dependent forces. And this was followed up by other very similar works. Now, a few things I was very quick on. And again, at a high-level description, you have to lie a little bit for clarity. It's not exactly lies, but the one thing I didn't mention is that the force is not in the z basis. So it's not spin up goes up, spin down goes down. It's in the x basis. So spin up plus down goes up. Spin up minus down goes down. It just turns out that's much easier, but the math and the physics is exactly the same. It's just a choice of basis. So our gate here is what we call an Ising gate, because there's an effective Ising interaction between the 2 spins that we want to entangle. So this is sort of a Hamiltonian here, and this is the evolution. The other thing you might have wondered about is, what about all the other ions? They're going to move around, right? Well, that's absolutely true, unless you do it really fast. And so this picture up here, things really get simple when you apply very fast forces. But if you go through the numbers, and if you make t to be much smaller than the period of motion of the collective motion of the chain, which is about a microsecond, by the way. So if you can do this in a nanosecond, that's great. But if you plug in the numbers and you put in a nanosecond for that, the delta, the distance you move, actually is big. It has to be big. It requires a lot of optical power. I think you probably need on the order of a millijoule in a nanosecond to do that. So that's a pretty beefy pulse that I'm very scared of, and I don't want that to be part of the system. But not impossible. And there's a lot of interesting research in speeding things up that make it simpler. That's a nice combination. It gets faster and simpler. Okay, so the gates are much slower, so we have to worry about all these modes of motion, unfortunately. But it's a classical worry. And basically, the way we get around this in a big chain is that these laser pulses, they're not just on and off. We pulse shape their amplitude, their frequency, and their phase very carefully, according to a pre-calculation that makes sure that all the modes of motion, they will be excited in general, but they all return to their original states at the end of the gate. And this is not hard to do. It's a classical difficulty. And so we pre-calculate these pulses. So I don't want to entirely sweep it under the rug, but it's a way to control all these ions using the picture I mentioned. And the fidelity of this type of a gate, now I think there is a 9 here. I think the highest fidelity of this type of a gate between ions comes from Oxford Ionics, using not lasers, but actually microwave fields. And they have 99.993, I don't know what anyway, there's another number here. So they're very high fidelity. These are the highest in any platform. Okay, it requires exquisite control of the fields. Lasers are a little harder to control, and that's why I think the microwave gave them an edge. All right, well, let's go back to school then and look at sorry, my animation didn't, I'll just bring it all out here. Somehow the animation didn't work right. So what do we have here? This is a Hamiltonian that is a state-dependent force. We're basically applying a running wave field. You might recognize e to the I kx here. Well, okay, this eta parameter is called the Lambdicki parameter. That's where the k is. And x is equal to x naught times the position operator. It's the position operator of a single mode of motion. In a harmonic oscillator, it's just a plus a dagger. And it has its own frequency in the Heisenberg picture. And we're applying a spin-dependent force that's detuned from resonance by delta. Okay, so when delta is equal to 0, this basically, when delta is equal to 0 and the motion is very tight, then we basically have what we call the carrier operation, which is just a spin flip. Sigma plus plus sigma minus. That's when delta is equal to 0. And if you want to think of it in this picture of the qubit down and up, dressed by, that's probably not the right word, but in addition, we add the vibrational levels on top of the 2-level system. Remember, this is 12 gigahertz, and the vibrational levels are a few megahertz or something like that. And so the carrier basically drives a spin flip independent of motion. And so it's a very simple operator. We see this from NMR. You can do this with microwaves. Fine, spin flips. That's how we do single bit gates. But more interesting is when we tune this laser detuning from resonance. If you look at, we're interested in stationary terms that arise. And if this is equal to omega or negative omega, if you Taylor expand this exponential, you're going to get stationary terms. So for instance, if delta is equal to minus omega, then if you look at this term here, no, it's this term. If that's minus omega, then we have a plus I omega t, but there's a minus I omega t here when you expand that first order, and you get an A here. So sigma plus A, and then sigma minus A dagger. Of course, in quantum optics from decades ago, that's called the Jaynes-Cummings Hamiltonian, a very famous, very simple coupling, one of the simplest couplings of two quantum systems called the Jaynes-Cummings Hamiltonian. We call that in ion trap language the red sideband because we've tuned to the negative frequency from the carrier, sort of in the language of frequency modulation, right? Carrier and sidebands. And if you calculate the Rabi frequency in the Jaynes-Cummings model, it goes like the square root of n. These are the overlap integrals, if you want, of the motional wave packet. If you learn this in terms of optics, the square root of n is the number of photons that carry the coupling. Unlike cavity QED and photonic quantum optics, we can tune to highlight many other terms in the exponential here. If we go to the other sideband, the blue sideband, delta is equal to plus omega, then we pick out the A dagger term, and we get, this is sometimes called the anti-Jaynes-Cummings model. So instead of exchanging excitation between spin and motion, here we're exciting the spin and the motion, and then de-exciting them. But sort of the same, similar physics, little asymmetry, it goes like the square root of n plus 1. That's actually very important, this asymmetry. If n is equal to 0, if you don't have any vibrational energy, then there is no red sideband because you can't lose any more. If you're in 0, there's nowhere to go. You can't go to n equals negative 1. Whereas the blue sideband, you can always go up. Of course, if you're in spin up, the blue sideband shuts off. Okay? So it's that conditional dynamics. That was sort of an old term. And we were just discussing earlier. I know it was exactly 30 years ago, which is 5 conferences ago here at Rochester. We had, after Serac and Zoller had published the idea of doing all this stuff, I was working with David Wineland at NIST in Boulder. I was sort of a junior professor, if you want, in his group. And in my project, we had been building entangled states for clocks, but we sort of figured out, independently of Serac and Zoller, that we could apply pulses to make entangled states for our clocks. We didn't recognize the universality of those operations for quantum computing, but, and this was the conference we presented those results for the first time. So this is the Serac and Zoller idea and our paper that came slightly after that. And the idea is really simple, kind of similar to what I said earlier. If we have, this is just a single qubit for now, and a single mode of motion, harmonic oscillators here. If we cool to the ground state and we store a superposition of up and down, here you go, alpha down plus beta up, ground state of motion, and we apply just the red sideband for what would be a pi pulse if you're in spin up. This happens, right? You go from spin up 0 to spin down 1, and you don't touch spin down 0 because remember, this red sideband doesn't do anything. So what you've done here is you've moved the information, you've moved the qubit from the spin to the motion. And the Serac-Zoller scheme prescribes on how we use that qubit in the motion that's delocalized. All the other ions feel that same motion. And then you can simply extend this simple operation to entangle 2 spins. That's the Serac-Zoller model. Now, I was very saddened to hear that Joe Eberly passed. He was a very good friend. And even at the time, he was very excited in this ion trap stuff because we were sort of doing cavity QED without a cavity. I mean, it was an ion trap. We didn't have any well, we had photons, I guess, but our laser beams were deeply in the classical limit. We had phonons, and they were under great control. We could start in a pure state, and we had this blue sideband that they didn't have in cavity QED, so we could make all kinds of different types of states. One type of state, a very simple one, is a coherent state of motion, and that's just the classical version of the marble going back and forth. Of course, in the space of energy levels of the phonons, the Fock states, it's a Poissonian distribution. It's easy to make a coherent state. You can simply suddenly displace the trap or drive it on resonance, just like you would pump up the energy of somebody on a swing set. And we measured the evolution in the same coherent state. Each experiment, we drove the blue sideband for a certain amount of time and just measured what happened to the spin. Well, this is what happened. We started in spin down, and we saw what's called a collapse and then a revival. Very clean data. It had been shown in Cavey-Hudi experiments of Hiroshi and maybe Kimball around the same time, I think. But this is super clean, and this is really Joe's work. He took pride, I think, in looking at very simple quantum models like the James Cummings and seeing something that was, I mean, when you look back on it, maybe it's obvious, I suppose, but it just didn't. I don't think anybody really predicted that you would get such a clean revival. And of course, as n bar goes higher and higher, that revival goes out in time. So a very interesting effect, and I remember him being very delighted when we saw it in such a clean way. But he didn't stop there. I told you about the blue sideband as well. He showed a wonderful theoretical proposal with his postdoc, C.K. Law, here at Rochester, how to synthesize an arbitrary pure state of motion. Actually, mixed states too, I think. But if you think of a pure state of motion and you prescribe all the amplitudes of the vibrational levels, well, how do you make that? I mean, it's easy to say what they are, but how do you synthesize it? Well, Joe and C.K. Law took the problem backwards, and they said, well, let's say we have the state, and then we sort of coherently collapse using alternating red and blue sidebands and carriers to bring all the population down. Right, so for instance, if you start in some random superposition and spin down, you can always lower this, by driving the red sideband, you can always lower the vibrational level by driving that one a pi pulse. Of course, any of the stuff here is a mess. I mean, it's very complicated, the dynamics, and you have to retain all the phase information of all these levels when you do that. But eventually, then you apply a carrier here, and a red sideband carrier, red sideband carrier. And if you pick the amplitudes and the phases right, it collapsed all the way to zero. So just reverse it. It's just brilliant, actually. I'm not sure what it's useful for. No, anyway, it's synthesizing an arbitrary harmonic oscillator. And Dave Wineland's group did this shortly after that, about 20 some years ago. Again, this is a technique that we all remember came from Joe. All right, so let me move on and motivate Klaus Molmer's improvement of Serac-Zoller. So this, again, is a little bit specific. Here we're going to apply the red and blue sideband at the same time. And I draw it, in this case, this is a two-photon Raman transition. That's not super important. But we're driving on near the upper sideband and near the lower sideband at the same time. And in this case, if it's a Raman transition, it's just a beat note. The beat note is on the upper and lower sideband at the same time. And when you add these two Hamiltonians together, you get simple spin-dependent force, as I said earlier. So it's a very, yes, there is you might worry about the motion appearing in A&A dagger, but I'm not sure, do I work that out or not? Yes, I do work it out. But I'm gonna make it even more complicated by considering many modes of motion. In this case, we have a sum of all the Rabi frequencies, all the ions that are being illuminated, very general here. There are spin operators and a double sum over all the ions and all the modes of motion. And we're allowing a global detuning here, and these are the mode frequencies. Yeah, a little bit of a mess. This is kind of a thick slide. Maybe let's go to the end. I wanted to show this because there's some interesting algebra in this Hamiltonian. If you want to form the evolution operator of this Hamiltonian, right, in grade school we're taught that it's e to the IHT, but that's only if it's a time-independent Hamiltonian. This certainly is a time-dependent Hamiltonian. If you do something called the Magnus expansion, you have a fairly useless infinite expansion of commutators of H with itself at different times. Well, of course it's not useless, but if you have to calculate all those terms, I would say, yeah, I guess it is useless. Well, the nice thing about this Hamiltonian is that it doesn't commute with itself at times, but its commutator is just a number. And that means that all higher order commutators drop out. So that's an algebraic way to see why why the magnus expansion is actually very useful for this particular case. And when you do the math, you find out that, yes, you get a time-dependent term with sigma x's, right? That's the spin operator. And here you have another term with two sigma operators. That's the Ising interaction I talked about earlier. And what we can do is tune the coupling, tune the laser drive. Let me just kind of repeat what I had there. We can tune the laser drives such that this term gets nulled. And so this is writing that term out. This is basically a displacement operator. And in phase space of each mode of motion, we're executing trajectories in phase space. We just need that trajectory to return where it started, and then integral over that is 0. And you're left with the Ising gate. And again, this is a derivative of the what we call the Mulmer-Sorensen interaction. But it also allows you to apply not just C-naught gates, but you can apply it simultaneously to many, many atoms and do something like a quantum simulation of an Ising model. Yeah, again, I'll just skip over that math. I did want to say that there's something just occurred to us a few years ago that's kind of interesting. We'll see if it's really useful in the long haul. But this is a phase space picture of that single mode of motion when we apply these displacements. And in this case, this is more following the Milburn version. It's silly to say it that way, the Milburn version of the Mulmer-Sorensen gate. But the Mulmer-Sorensen gate involves a detuned force so that we execute circles in the phase space, in the rotating frame. The Milburn version is on resonance, so red and blue sideband, red on resonance, but we change the phases of the field so that we close a square in phase space. And so in this case, we'll enclose a square. It has area AB, and let's see. If you think in terms of displacement operators, and many of you are quantum opticians, you're very familiar with that. Basically, the evolution operator is just 4 displacements. Now, these 2 displacements, they commute with a phase factor. Well, any displacement operators commute, but you get a phase factor if they're not parallel, and these are at 90 degrees, and you end up with this phase factor here. And of course, these displacements, they cancel, and you end up with just that. Alpha, beta, these are spin operators. And so this is a very quick way to see that you get that Ising interaction, okay? And I'm pointing at this because we recognize that we can extend this by having a spin-dependent squeezing operation, a quadrature squeezing operation. And in this case, we don't have a state-dependent displacement, but we have a displacement. We need to run around in phase space, but it doesn't have to be state-dependent. And in this case, there's 8 operators. We displace, squeeze, displace, unsqueeze, displace, squeeze, displace, unsqueeze. So the squeezing coordinate returns to its original state, and the displacement returns to its original position in phase space. And if you look at these 8 operators, it looks like a mess. Here's the squeezing operator. It's a different algebra. It has A squared and A dagger squared. But these 3 things contract to a displacement with an argument that is exponentially enhanced or suppressed. That's squeezing operator. And now you look here, we have something like we had here. So we can then commute these 2 together, and we get basically a phase. But the phase now is exponentially sensitive to the amount of squeezing. And so you basically, and that squeezing operator contains spin operators. So that's a long way of saying that we get everything. We get a Hamiltonian that's a polynomial in all of the spin operators. So it's an n-body interaction. And we demonstrate, we can demonstrate this in ions. It's almost a software switch. Instead of tuning to the upper and lower sidebands, we tune to the second upper and lower sideband. Simple as that. And we realize this Hamiltonian here. So it's almost a software switch. It's a very powerful way to think about having better expression in your tool set of gates. And we demonstrated this on a very small system, and as usual, fidelities weren't to kill for. But the amount of squeezing, whenever somebody says squeezing, I'm usually tempted to say, well, all right, you need 80 dB of squeezing to make it useful. Well, you only need a few dB here because you're taking advantage of the nonlinearity, not necessarily the amount of squeezing. So these both efforts only involve like a dB of squeezing, very little. But we're able to gain a many-body type of interaction that we can measure. Okay, so I need to start to wind up. I wanted to talk more about some optics, but this is a system that we built, took its final form probably 5 or 6 years ago, where a typical AMO lab was sort of kind of dumped into this box. If it were only that simple. Everything that needs to be adjusted in here, there's a vacuum chamber, an ion trap, and a bunch of laser beams. But it's all done with motor mics where needed, and the box is closed for many months at a time. Calibration of this system is really hard, but it's mostly done in software. And it has a capacity of 32 qubits. Actually, we can hold many more qubits, but we only have 32 laser beams. Like those tweezers I showed you early on, we only have 32 of them. But it's a fully universal programmable quantum computer. The fidelities are not quite industry standard, but something like 98, 99%. It's not too bad. And this was early on funded by IARPA, and more recently it's been taken on by the Quantum System Accelerator, a DOE center, and the NSF STACK program that allows us to co-design algorithms to this machine. This funding allowed us to work not only with Sandia, but also these mostly laser companies that could make dedicated hardware, not for the usual use, like the L3 Harris team. They make wonderful AOMs. They're very expensive. And they make multi-channel AOMs that are amazing, but they're really expensive. My colleague Jungsang Kim at Duke is always interested in making things smaller, not just to be cute, but when you make an optical system smaller, it also is better performing. And so this is his latest vacuum chamber, where the chip is the vacuum is sealed right on the chip with an indium seal. And actually, there is a small ion pump not shown here. It's really small, one of those small guys, and it has really good vacuum, 10 to the minus 11 or something, high 10 to the minus 11s. So I won't get into detail. This system, we've used it for all kinds of things over the years. And again, you're not intended to read this, but we're very busy working with lots of collaborators. Many of them are in condensed matter theory. They want to study some exotic spin chain dynamics or maybe a phase transition in some exotic theory of magnetism. And so that's been a lot of fun, just learning about different fields. And with a programmable system, what I notice is that we don't have to think about the atoms or even the lasers when the thing's working. We think more about how to compile the gates, how to think about mitigating errors, how to do things at a much higher level. And the NSF STACK program sort of is acknowledging that vertical sort of interaction between all these different fields. I want to now close over the last few minutes about how are we going to scale? I mean, 32 is great, but we really would like 32 million, of course. More qubits are always better. And I think no matter what the platform of a quantum computer, it's going to be modular somehow. I think when you build a quantum system big, it just notices itself. It loses coherence. And this is where optics is going to play a central role, I think. And so this is sort of obviously a concept picture where you have a bunch of, these could be ion traps, they could be neutral atom systems, even quantum dots. But a subset of those qubits are connected to an optical fiber, and the photon is allowed to use as a conduit to mediate entanglement between different parts of this network system. I'll get into more details on that in a minute. And so Jungsang Kim, Ken Brown, Lu-Ming Duan, Peter Mounds, and I, a few others, published sort of this architecture paper. We see a lot of those nowadays. But this is 2013 or 2014, how you might, a conceptual picture of how you might build a scalable modular quantum computer. And as it turns out, this fellow visited my office shortly after that paper, and he's a venture capitalist. And he literally said those words. He said, this reads like a business plan. And he basically eventually convinced us that we should start IonQ, which is a company that's going to build these things for many reasons to connect with customers, but also to scale. And it's getting so expensive that it's hard to do some of this scaling at a university. I'll freely admit that. The good news is, there's a big industrial play in quantum computing now. We all know that. And while I and everybody else has a hard time hiring postdocs, it's still good for the field. I do believe that. I'm not a zero-sum person. Partly, if they all crash, then there's going to be a flood of postdocs for all of us. But so that's the good news. And if they don't crash, that's even better news, because then our lives are much more valuable as researchers on a new technology. So I'll fast forward to a couple of years ago when the company actually went public, which I still look back on it and think it's a bit ridiculous, but it's a pure quantum company, the first one that went public. And again, the market is what it is, but they're sort of a behemoth now. They're about 500 people, and they're sort of sucking up companies left and right now. So what about scaling? Well, it's going to take a budget for sure. But with trapped, now returning to kind of reality in trapped ions, in trapped ions, there are many opportunities for scaling. One of them is pretty well known. Actually, Dave Wineland and Dave Kopinski sort of pushed the idea of a QCCD, quantum CCD. You move individual atoms around. And that, in a sense, has modularity, very interesting. The company Quantinuum, which spun off from Honeywell a couple years ago, they've taken this the furthest, where they have, I think on the roadmap, they're probably right here, where they have very complex ion traps where the ions can be shuttled around. They don't deal with big chains, they deal with 2 ions at a time. It's actually very simple. And the 2 ions they want, they bring them from the reservoir, and then they entangle them and bring them back. It has a scaling problem, because as you make the system bigger, you're going to be spending all of your time shuttling stuff around and not doing your computation. Yeah, whatever, but it's a way to scale, maybe to a few hundred, maybe a few thousand qubits. I don't know, we'll see what the numbers are. But you can't shove 1,000 qubits in a single ion trap. That, I should never say never, but I think that'll be extremely hard. Oxford Ionics, I mentioned them before, they have very promising plans to put hundreds or many tens of thousands of ionic qubits on a single chip. And the cool thing about their plan, again, is there's no lasers in the gates. They use lasers for spam, readout and initialization, but the gates are mediated by microwave fields, which are, they call them electronic gates for obvious reasons. And so that's really interesting, and they're now combined, and Oxford Ionics is soon to be part of IonQ. So it's very interesting what's going on there now. I want to talk more about these modular connections that I mentioned earlier using optics. Here's another PowerPoint slide. It's so easy to draw these of a large-scale quantum, a large-scale architecture. But when you look at the architecture of this, we have fully, I didn't mention this, by the way. In a chain of ions, remember that 1 over r cubed? Sorry, I forgot to mention that, 1 over r cubed. Well, if you couple to all the modes and you use that classical control of those laser fields, it's all-to-all. You no longer have distance depending. So within a chain, you have all-to-all connections, which is a very powerful sort of microarchitecture. But it does have a limit, and we're going to have to use some way to get out of that. And in the optical incarnation of that, we could imagine a subset of these ions in a single chain are optically active. They produce photons, and in this graph of there's only 64 qubits here, 8 by 8. We can connect any green qubit to any other green qubit with a constant cost. Only 3 operations to do that. And so architecturally, we're not enjoying this advantage yet, but when systems get big, this will almost certainly play a role. And we can play around with other architectural niceties, like having a buffer where we can make it synchronous, doing things like entanglement purification, which takes extra qubits and so forth. But let's dive down into the physics of what's going on here. So how do we map an ion qubit to a photon? Well, it's fairly easy in some systems if you're willing for it to be lossy. So let me explain. If we have a qubit, spin down and spin up, very stable, and we excite with, say, a fast pulse, it's going to come back down to either that state or that state. In fact, we can make this 50-50. It doesn't have to be. But it's 50-50, and the photon that results is actually polarized differently. So now we have, in a sense, a post-selected entanglement between the spin and the polarization of that photon. And if we do this twice, and by the way, the probability of collection, you have to collect that photon. And if we do this twice and port this on the inputs of a beam splitter, simple 50-50 beam splitter, we have Hong-Mandel interference that when we detect coincidence photons here, we can say that the 2 atoms are now entangled. So it's no longer probabilistic, it's heralded. You just have to wait long enough, okay? So most of you are probably familiar with this idea. And it was, again, first discussed by Hong-Mandel and Shi and Ali a long time ago, and demonstrated in all the optically active quantum platforms. I've probably missed a few here. What's very interesting, the quantum optics of the beam splitter, when I first learned this, I just couldn't believe how beautiful it was. Actually, the result comes from Schwinger, of all things. But the idea of 2 ports on a beam splitter is that you can transform the bosonic operators of the photon to an effective spin. And that effective spin is basically depending on how many photons you had in both ports. And the act of the beam splitter is simply a rotation of that angular momentum operator. It's really wonderful math. There's a lot of group theory behind it. There's an analogy for squeeze states. It gets a little harder. But for 0 photons, okay, it's pretty boring. Two vacuum states result in 2 vacuum states. For a single photon in either path, it's sort of like a spin 1/2 system, because we have 1 photon total. And so we have basically akin to a single qubit rotation between where's the photon? Is it in mode B or mode A at the output? For 2 photons, this is the Hong-Mandel interference. When we have 2 photons impinging on a 50-50 beam splitter, it's this middle line that we want to pay attention to. 2 photons, and when theta is pi over 2, reflectivity is 50%, theta is pi over 2, we don't get this. So 2 photons never appear on opposite sides. This is the Hong-Mandel effect. They always go together. And the physics behind this effect here that allows us to entangle, well, we're detecting 2 photons on opposite sides. That can only happen if the photons were different polarization, different modes. They don't see each other, okay? In a sense, the beam splitter erases which path information on what atom emitted what polarization. Okay, so this is the tool. This is a little bit of a history of trying to do this to entangle qubits. This is just the ion systems. It started a long time ago. I was at the University of Michigan at the time. This is 10 to the -3 per second. So it's like a dark matter search experiment. So that gets everybody upset. But we've really, just by doing better optics, thinking about the problem better, we're now at about a couple of 100 hertz, which notably is only 1/50th of the I always get those two, intra QPU gate, the Mulmer-Sorensen gate. So it's not so much slower now. That's great. And if you look at the entanglement rate versus the fidelity, these last three or four points are just over the last couple of years from Oxford and our group at Duke involving these ions. Again, the fidelities are not super high. Oh, I wanted to, there was another IonQ absorption here. The company LightSync aims to change p squared in this architecture. Too many animations. That p squared, if you could put a memory in the middle of this, you could hold on to one photon while you're waiting for the other, p squared becomes p over 2. And the company LightSync is using silicon vacancies in diamond, very well coupled to optical fibers that can be put in an ion trap, it looks like. And we may have other inefficiencies, but they're not enormous. And this will be a big, big gain. So that 1/50th is probably going to become about 1 before too long. So then it becomes viable to really think about exploiting these more. And with that, I'm going to go really fast at the end. I do want to talk about this for a minute because Gerard Loix gave a very nice talk yesterday on recoil effects. And you might wonder, well, what about, doesn't the recoil effect tell you which path? Well, if it's a 2-photon protocol, no, because both of them emitted the photon. So you don't know which one recoiled. But to get high fidelity, we need time bin photons. So we actually need to make a superposition of the qubit, make a photon, do a swap, make half a photon. I shouldn't say it that way to this crowd. Let me start again. So we make a superposition of the spin states, and we attempt to make a photon if the state was down. Then we do a swap, and then we attempt to make another photon if the state is down again. And so we should have a superposition of early and late photons. Now, these early and late photons cause recoil, and there's intervening evolution of the atoms in the trap. So you have to phase those time bins so that you don't see the recoil. And we saw this effect. Like every quantum experiment, the first thing we see is a flat line when we're expecting a nice big sine wave. And we saw that flat line, didn't understand why. And it was because the time bins were not synchronized. They were getting killed by recoil errors. But we fixed that, and just kind of interesting that, I mean, we should have seen this. We should have called you, Garrett, and maybe you would have told us right away that. that allows us to get very high fidelity, and time bins are going to be useful to go over large distance as well because they're less sensitive to birefringence and so forth. So at Duke, we have 3 nodes here. One of them is very special. It has very high numerical aperture to be polite, and we're right now working on a 3-particle p-cubed experiment, so we're going to be back to a 10 to the minus 3 per second, sorry, just for a little while. So the grad students aren't happy about that. But it'll be a p-cubed heralding, triple heralding of a GHZ state between these three ion traps, Alice, Bob, and they call it Cleo. Should have been Charlie. I don't know why they called it Cleo. Okay, so let me now start to pull out. I will skip over these things, sorry, and go right to the end. At a very high level, I always show this slide because I think the future of this field, universities really can't do it alone. And currently, industry sort of, I don't want to say they don't have a guide, but I don't think they can do it alone either. There's a lot of research that has to happen. And this interaction is very interesting. I think that there's room for something else. Maybe it's a government lab, maybe it's, I don't know what it is, but maybe it's some type of an institute that's aligned with everything needed for quantum. And so I think the National Quantum Initiative, I'm seeing Mike Raymer here, he and I sort of went to Washington for a few years ago to argue this idea that we need much more concentrated efforts in certain areas. And the National Quantum Initiative was a result of that. And it's going strong, and we have, I guess it's under renewal now. All signs are that it will be passed, and these centers will continue. But it's going to take time. It's a real long play. And the quantum computing is a field that is fairly unique in terms of there's not yet a market. We don't even know what these things are good for. But we do know there are certain problems that we'll never solve without quantum computers. I think that's fairly safe to say. We can go on as a society and not solve them. That's fine. But if we're going to solve them, they will involve so much space that Hilbert space is the only place to do it. So it's tricky developing a new technology when there's no obvious market. So this is sort of where we are. All right. With that, I will put a cheap ad for our Duke Quantum Center in downtown Durham, where we actually have several systems that we run full stack research from software all the way down to atomic physics. And we also have neutral atom trappers there and interested in growing in other objective quantum systems. Thank you for your attention.
Thanks so much for the talk, Chris. There's time for questions.
Thank you for a very informative and thought-provoking talk. I have a question that it's a technical question that connects something from earlier in the talk, later in the talk. So as we're talking about the gates and the need or lack of need to cool down to the ground the photons state, and then the shaping of the pulses. Would that shape be easier if you were in the ground motional state? What is a typical photon population in your systems? And then later you mentioned that Oxford Ionics uses microwaves. Is it easier? Do you also need to shape those? What are the timings of those pulses compared to laser pulses? Thank you.
Okay, so I'll try to quickly answer that. The first question concerned the localization, and this comes down to the something called the Lamb-Dickey limit. Now, for the Serac-Zoller model, you needed to be in the pure state of motion. You needed to be n equals 0. But it turns out for this expansion to work, we need to be able to ignore high-order terms. And the expansion is eta. It's called the Lamb-Dickey expansion, and I sort of, in this expression, I guess nowhere else, I included sort of the next order term. And you can see as long as n eta squared is really small, and that means that you're, it's not obvious from this, that means you're in the Lamb-Dickey limit. It means that the localization is small compared to a wavelength. And the wavelength is half a micron or something like that, maybe smaller than that. So as long as you're a few tens of nanometers localized, doesn't have to be a pure state, then this is valid, and the Mulmer-Sorensen and Milburn versions of these gates only require the Lamb-Dickey limit. Otherwise, it depends on n, and it's effectively like having noise. Okay. Your second question concerned microwaves, and the way I look at microwaves, basically we're exploiting an electric field gradient here. This is e to the I kx, and it's the kx term that matters. It's that spatial dependence. And again, because it's a sine wave, you have Lambdicki terms. A microwave field, if you have a running wave, you also have e to the I kx, but now k is really small, the wavelength is huge, and so the coupling is going to be really small. You won't even get the leading order term. So what they do is they have not free-running microwaves, but it's near-field microwaves, because the atom is on top of a chip, and you put microwave fields, and you will have a length scale associated with the altitude of the ion above that chip. So that could be 30 microns. It's still larger than a laser, but the cool thing is that it's not a sine wave anymore. You don't have a Lambdicki. You can make it very linear. So it's almost, there's no curvature beyond just this, there's just a gradient. And so this expansion is even better for microwaves. And pulse shaping of microwaves, the time scales are very similar to this, actually. They're tens of microseconds. And so you could argue these systems are slow. And yes, they are. Yes, they are. No matter how you cut it, ion trap gates will be slow. I had a slide showing that, well, if you do error correction and you have to measure and you don't have high fidelities, you're going to be slowed down anyway. And ion traps, you know, our measurement is nearly perfect. I didn't talk about that. And we're going to be doing less error correction. So it's not clear exactly who's going to win in the end. But ion traps just will be slow, especially the photonic interconnects. So microwave pulse shaping is really easy at that speed.
Thanks. Good tutorial. I wanted to follow up on microwaves. So I don't quite see how the 2-qubit gate works when involving microwaves. I presume somehow it was still involved in local.
Yeah.
And then the other is, can you comment more on how localized microwave excitation is? What is the impact on crosstalk?
Yeah, so this is I think I had it here. Yeah, the Oxford Ionics work that the idea is that atoms are put on a 2D grid, like a chessboard or something, and there's local control of their position because the chip has a bunch of electrodes, several electrodes, and it's very clean to move one atom next to another one. You can merge them. And again, you don't even have to keep them very cold. I mean, they don't have to be near the ground state. And when you do that, they're in proximal motion. You actually, then you move them a little bit off axis so they sample a non-zero microwave field. Now it's a position-dependent field, which is exactly what the Mulmer gate was. So it's the same physics there. You have to, I think it changes the laser control, no lasers, into positional control of the atoms. That's really important. And I believe I've gone through some numbers, and it's a little worrying, but you need 10, 20 nanometer control of the positions of these ions.
So it's not all-to-all connectivity, like
it's highly parallel, but it's just, yeah, it's a 2D nearest neighbor graph, but it's highly parallel, and yeah, so it's adaptable for surface code and things like this. So. And again, I'm on thin ice here because it's really Chris Balance and Tom Hardy at Oxford Ionics that have really kind of pushed on this. But in that platform, they've realized these very high fidelity gates. Looks very interesting.
For final questions?
I'm pretty sorry that it's not the focus of your work, but I'm still curious about the crosstalk.
Mm-hmm. So the microwaves, there are nodes of microwaves above the chip, and that's almost the entirety of the work is to make sure that the atoms are on those nodes. And so the crosstalk really has to do with the fact if you're moving these ions, do these ions feel the motion, and by how much? And that's the kind of the tens of nanometers dimensions I mentioned before. But you're right in the sense that so far the demonstrations have not been to scale. And we're just going to see. I have a feeling in the back of my head, don't quote me on this, but there's going to be some limit that nobody can write down. And it's probably going to be between several hundred and maybe 10,000, I don't know. I don't see a problem to get to many hundred, though, at these fidelities.
All right.
Okay.
Thank you.